So in this video, I'm going to be writing some Python functions to calculate the friction factor, to calculate head drop given with a given flow, and then working backwards to calculate the flow we need for a given head drop. And so before we move to Python, I'm just going to write a couple things on the whiteboard to help us conceptualize kind of where we're going and the functions we need to write. So here I have Bernoulli's equation written out, and in order to get it into head drop form, we just need to divide across by g, which is the acceleration due to gravity. So doing that, we'll have g in the denominator on the right side of the equation. The g will cancel out in this term, and then we'll just have it in the denominator on these. And so for our scenario, we have a set pipe, and the pipe doesn't have a change in diameter. So this term will always be 0. And so what this kind of shows is that we can get the head drop by either having a change in height or a change in pressure from a pump or some other different way. And so what we're first going to write is we're going to calculate the friction factor, and this can be done kind of using the relationship that we used in a past video, which is just that 4 times the fanning friction factor times the length of the pipe over the diameter of the pipe times velocity squared over 2 equals the frictional heating. And so again, since we want to get at the head drop, we can just divide both sides by g. And then we'll be writing an equation, or we'll be using Churchill's equation, which I'll talk about a little bit later on, to calculate the friction factor. We know the diameter of the pipe and the length of the pipe. We know the acceleration due to gravity, and then we'll either be given the flow, and we'll be able to find the velocity, or we'll be giving head drop and work backwards. So how we'll be able to find the velocity is this relationship, that the flow is just the velocity times the cross-sectional area. And since we have a circular pipe, this can be rewritten as the velocity times pi d squared over 4. And then we'll be able to rearrange this equation. And find velocity. So when we're given flow, we'll be able to find the velocity, and we'll know all the other terms, and we can get head drop. And then when we're given head drop, we'll just have to work backwards and find this flow. So now I'm going to go ahead and move over to Python and write these functions. So now that we know the functions that we'll need to code for this homework assignment, and we have the relationships that we'll need to use, we can go ahead and start coding them in Python. So I went ahead and I imported NumPy because we'll use that to compute the friction factor. And I also imported SciPy's optimize because we will use that later on for our function that determines the flow for a given head drop. So like I said, the first function is going to be computing the friction factor, and we are going to use that using Churchill's equation. And so if we take a look at Churchill's equation, I have it pulled up right here. It is just one of the equations that can be used to compute the friction factor. There's many other ones, but we're using this one because it's probably one of the most accurate, and it can be applied to laminar and turbulent flow. And so I'm just going to go ahead and copy this over. So for this equation, we'll need to supply Reynolds number and the surface roughness. And then I'll go ahead and define theta 1. and then define theta 2. And then we just need to return Churchill's equation. So I'm going to only return 2 times Churchill's equation because this equation set up for the Darcy friction factor, and we're working with the Fanning friction factor. So 2 times all right, now we can go ahead and test if this function works. So if we pass a Reynolds number of 1600 and a surface roughness of 1 times 10 to the negative 3, we should get a value of 0.01, and we do. So the function for that works. So now I can go ahead and write the function to calculate our head drop. So I'm just going to define it as head drop, and we need to pass the flow that's given, the length of the pipe, the diameter pipe, and the surface roughness. So from here, we can just use the equations that I had on the whiteboard, starting with the one for velocity, which is just going to be flow times 4 times the volumetric flow divided by pi times the diameter squared. And then we can calculate Reynolds number, which is going to be rho times the diameter of the pipe times V divided by mu, which is the viscosity. And then we can use the function we just wrote to calculate the friction factor. And then we can return the head drop, which is just going to be 4 times the friction factor sorry about that, 4 times the friction factor times the length of the pipe times the velocity squared divided by 2 times the diameter of the pipe times G. And now before I go ahead and run this block, we need to come up and define some of our constants. So rho is we're just going to use the density of water, which is 1e3 kilograms per meters cubed. The viscosity of water, which is 1 e to the negative 3 Pascal seconds. And then gravity, which is just 9.81 meters per second. So now we can go ahead and test our head drop function. So if we pass 0.1 as our flow rate, 10 as the length of the pipe, 0.1 as the diameter of the pipe, and these units are all in meters. And then for our surface roughness, we can do 5 e to the negative 3. And this should give us about a value of 25. And it doesn't. That is great. Let's see, what is my issue here? All right, so after a little bit of troubleshooting, I had an error in computing theta 1 for Churchill's equation. I had this expression was supposed to be all in the log, and because of the way my parentheses were, it wasn't. So I went ahead and fixed that, and now our head drop function works as it's supposed to. So now we can go ahead and write the function for our flow. So I'm going to go ahead and define our function as flow rate, and we're going to pass our known head drop to it, and then the parameters of the pipe, so the length, the diameter, and the surface roughness. And so now to calculate the flow rate when we're given head drop, it's a little bit different because we need to find, we don't have an expression for velocity. That can't be calculated because before we used Q that was given to calculate the velocity, and then the velocity was used to calculate the Reynolds number, which was then used to calculate our friction factor, and then both of these were used again to calculate the head drop. So actually how we're going to do this is kind of working backwards, and we're going to use root solver. So at the start of the video, I had it imported up top, and to use root solver, we need to define an equation that we will pass to it. Root solver always takes in a vector of unknowns and returns the answer as a vector, so we need to keep that in mind as we code. So I'm just going to call our vector y, and then the only unknown in our vector is the flow rate that we're looking for. So we just need to go ahead and pull that out. And then what we need to return is when Q gives the head drop that we're looking for, we'll subtract it from that head drop that we know that we were given. And when that equals 0, then we'll have our accurate flow rate. So all we need to return is the head drop minus the head drop that we calculate with our guess Q, which can be used, or which can be done with our head drop function that we wrote above. So I'll just pass it the same parameters, and then since we're using root solver, I need to make sure we return it as an array. So now we can just go ahead and implement the root solver and pass our equation to it, and then we also need to pass a guess for Q. So this is a little difficult, but we can actually derive an expression for this, and I went ahead and took a picture of the derivation on the whiteboard, and I'm going to talk through it a little bit. So we know the head drop is equal to the frictional heating over gravity, and we can go ahead and implement the expression for frictional heating that uses the fanning friction factor, which is the second line here. And then from there, just using algebra, I went ahead and rearranged the equation to solve for V, and then used the relationship that the flow rate is equal to the cross-sectional area times the velocity. And so the cross-sectional area, since we have a circular pipe, is just pi times d squared over 4. So we can go ahead and use this expression to get our Q guess. So our Q guess is going to be equal to pi times d squared divided by 4 times the square root of the head drop times the diameter times gravity divided by 2 times our friction factor times the length of the pipe. And so since in this function we can't use V to calculate the friction factor, I'm just going to go ahead and make a guess. We don't have to derive an entire expression for it like we did for our flow rate guess, because the fanning friction factor kind of has a small range, and so we can just go ahead and guess a number in this range. If you take a look at the Moody diagram, right in the middle is about 0.01. So we can just use this, it'll work as an accurate guess. Make sure I have that in our expression. And then we can go ahead and give this guess to our root solver. And then before we're completely done with the function, we need to make sure that we get the answer out of our root function. And to do that, we just need to grab the first element of the x attribute. So now I can go ahead and run this code, and then we can test our flow rate. So for the head drop that we were given, I can just go ahead and use the head drop that was calculated from our function before. And if our flow rate works properly, we should get the given 0.1 or something very close. So then what's left is just the parameters of the pipe. And so the length is still 10 meters. Our diameter is 0.1 meters. And then we'll use the same surface roughness. So we go ahead and run this, and we get a value that is extremely close to 0.01. So that function works. So here we have a function that is used to calculate the friction factor. And then we have this function, which calculates head drop when we're given flow rate. And then our third function calculates the flow rate for a given head drop.